Hello, my name is Rob Sides. I'm the Director of Marketing and Product Management for Ametek Scientific Instruments. You may know Scientific Instruments through its brands Princeton Applied Research, Solutron Analytical, Signal Recovery. Today I'm going to talk to you about electrochemical test methods and products for the evaluation of lithium-ion batteries. This is going to be a very focused presentation today, and I'm going to highlight the VersaSTAT and speak about its function through VersaStudio, its data acquisition, data analysis software. So the field of electrochemistry really hits many different types of applications, and we kind of think about these as three different groups of research. One being the energy researcher, others being corrosion and physical electrochemistry. We're seeing a tremendous amount of interest in research in portable power. This is all at our government labs, at our industrial partners, and key academic researchers. But the energy field is very broad. It is there's sub-segments into batteries, capacitors, fuel cells, and solar cells, and each one of those researchers have their own needs for data acquisition, data analysis. Today's focus is going to be on lithium-ion batteries in particular. So what type of battery research trends are we seeing in the market, and what type of requirements do these researchers need to kind of help advance the science? One's going to be material development as we look to from R&D levels to moving into larger cells and stacks for increasing requirements. And we call out here some typical sizes and required for testing small coin cells all the way up to larger EV battery packs. Other hot topics of research is SOC, that's state of charge, and state of health of low impedance stacks. Traditionally, this is where electrochemical impedance spectroscopy can really add tremendous value. Another hot topic of research is providing spatial resolution to these types of measurements and doing different types of in situ measurements. These traditionally go along with our VersaScan three-dimensional positioning system. But let's wrap some numbers. Let's talk about some numbers, and let's talk about the trends that I see in lithium-ion battery research. Let's do that in a way that we're going to do some definitions and use something that we're all familiar with. We're going to reference the size of cell phones. Look for trends in battery research as they relate to consumer products such as cell phones. So we're going to be able to think about batteries in terms of capacity, and capacity is really the amount of charge that the battery can store and deliver. And we're going to normalize that to the size of the battery itself. So when we think about in terms of batteries, we'll think about charge in the term capacity in the units of amp hour or milliamp hour. Here's some data I put together, and it shows the different battery sizes and trends in capacity between the BlackBerry, the iPhone 5, the iPhone 5S, the iPhone 6, and then some details on what a laptop or electric vehicle battery looks at. But if we look at over here on the right-hand side, we can see, what do we see? We see 1100 milliamp hours out of a BlackBerry, and then 1434, and then 1560, and then 1810 milliamp hours out of the iPhone 6. So we know this. We see this as consumers. We know that we have more and more demands for power as we ask our phones to do more and more. We want the not to sacrifice battery life as we're getting more and more power and out of each device. And you can see why this continues to be a hot topic of research, because it's really trying to solve a portable power puzzle. How can we deliver more power per charge and be longer lifetime? You don't avoid capacity fade over the lifetime of the battery. So I said even within batteries, we see subsegments in materials development. This is kind of the R&D level. We talk about cathodes. These are your high voltage transition metal oxides. Anodes, typically now carbon-based materials. Electrolytes, lithium-ion salts, and separators. So those are really the four components to a battery. And at the material level, the R&D level, there's certainly research going on in each one of those four areas. And then they scale up from battery materials. We talk about coin cells and 18650s, and these may happen in sealed batteries. out on the desktop, and that may be in 2-electrode mode or 3-electrode mode. And then as we grow up from single cell batteries up to the battery requirements of laptops and cars, how we're going to have the same battery technology that drives your remote control at your house. How's that going to drive your electric vehicle? And that's simply by stacking several of that similar battery technologies together to achieve higher currents or higher voltages and current and voltage, and that's going to give you the power. So let's talk about typical DC analysis techniques for lithium-ion batteries. The first one we'll talk about and show some data on the next couple slides is cyclic voltammetry of anode and cathode materials. And so this is really mechanistic studies, or if I'm looking at electrolyte, I'm trying to determine a voltage window, but these are typically done in half-cell environments, and I'm looking to work inside an argon-filled glove box. Once we kind of develop that technique, kind of prove out those materials and they're going to function in the voltage ranges that we need, we use those voltage ranges to set up charge-discharge experiments. These are galvanostatic control experiments, so my signal is going to be a constant current, and I'm going to measure the response as a voltage. I'm going to do this to study the coulombic efficiency, so coulombic being charge, and the efficiency being what is the ratio of charge I get out of the battery versus the charge that I put into the battery. And of course, we want those charges to be as close as possible, because we want a very efficient battery that gives me as much as I give it. Cycle life. We're going to study cycle life by studying the capacity. Now remember, that was in milliamp hours versus cycle number. And so this is going to tell me not just how does my battery perform on day 1, but day 30, day 90, day 100, day 1000 is their cycle by cycle levels. And I'm going to be able to study the effect on charge rate, on the capacity or cycle life. When we talk about charge rates, we think about this in pulse power applications. So if I need my battery to deliver more power, whether it's during a GPS tracking on your phone or whether it's through acceleration in the vehicle, we're going to need to charge discharge that battery at a higher rate to mimic that protocol. And then we can calculate out the capacity using specific energy, specific powers. Another a variant on that typical technique is a charge-discharge with voltage hold. And so what that's going to do is, as you charge the battery, it's going to reach a charge cutoff from potential, and then it'll allow us to switch over to a potentiostatic mode and hold that voltage at that level and make sure that we can kind of what we call trickle charge the battery. And so we can make sure the battery is fully charged into a completely charged state before we start discharging it. So let's move over and let's talk about cyclic voltammetry for battery material investigations. I've got a couple different chemistries shown here. If you are new to this type of research, one of the things that you will see first, striking to me when I was doing this research in lithium-ion batteries, is really first to think about how slow the scan rate is for a typical lithium-ion battery cyclic voltammetry experiment. And this may be on the order of 0.1 millivolts per second, very typical. Some tests are even slower now. But if you think about how a battery is being used, what are you functionally doing? You're sweeping a voltage from a totally discharged state to a totally charged state. So you're functionally charging and discharging the battery over a given period of time. And so my voltage window I have here in the first experiment is 3.4 volts to 4.5 volts. And if I go back and I look at something like that, and I say that's going to be 1.5 volts, and that's going to take 0.1 millivolts per second, that's going to be 15,000 seconds. So that's going to be, what is that, a little over 4 hours. So that is a C over 4. That's equivalent to kind of like a C over 4 discharge rate, so a very typical rate of when testing within battery work. Another thing to point out is, when we think about batteries, we often think about very high currents, need a lot of power. But the researchers and materials, when you're synthesizing these new materials, we don't synthesize a lot at one time. It's a very precious material at this point in time, and so what we're going to do is you'll see much smaller currents associated with studies in this subsegment of the energy market. and when you look here, at this lithium manganese oxide, it's going to be this cell that I have here is less than a milliamp, and then a lithium iron phosphate cell down here on the bottom right, and it's just over a milliamp. So traditionally, we may think batteries are all about high currents, but a lot of the coin cell work is done in that kind of milliamp type current ranges. But as we move on beyond cyclic voltammetry, we really want to highlight some of the specific actions that we have within the VersaStudio energy techniques that really allow you to kind of customize the signals and control modes that are common to electrochemical studies. How can I make them specific to energy techniques, energy studies? And we've done a lot of things recently with product improvements to help you out here at product developments in our software platforms. So some of the things available in these energy techniques, and all of the techniques are listed on the left, and some of the graph templates shown. But really, what we're going to do is we're going to highlight industry terminology. I'm already going to start introducing terminology like C rate, and then I've already spoken a little bit about capacity. And so this allows you to input those values and outputs using those terminology associated with that field. Default instrument properties tailored for the application, some different specific graph templates for data analysis. We'll talk about how you can accumulate the charge during a voltage hold experiment, some data resolution that will manage the amount of data flow coming in through the experiments, and then we can do some really complex signals based on constant power or constant resistance. So let's speak about each one of these into a little bit more detail. We're going to have I've defined capacity in the previous slide as milliamp hours, and it's really an engineering take on the measurement of charge. And when we take this and we can normalize this to the current applied, we can get the C rate. And when we talk about C rate, we talk about the amount of current it would take a given battery to fully discharge over the span of 1 hour. So if it's going to take 1 hour to discharge your battery, that current is going to be 1C. If it's going to be how long does it a current to discharge your battery over 2 hours, it would be a C over 2. Energy actions allow the limits within VersaStudio to either move to the next step in the experimental sequence or to terminate the tests. We can input those based on potential, capacity, or a lot of different types of parameters. And so this is how you would do a discharge to less than 3.2 volts, and the next step would be a charge and go and exit out when it goes to be greater than 4 volts, for example. Something I will talk about now is the default instrument properties. I told you that we have VersaStats being used today by every different type of application in electrochemistry. We have a lot of our users are in the fields of corrosion and physical electrochemistry or energy. But the VersaStat itself gets set up through some of its instrument properties differently depending on which specific action you select. And so what our global application team does during the product development is to go in and actually run tests just like our researchers do on some of these different lithium-ion batteries of different configurations and chemistries. And what we have done is identified the most common instrument properties that help set up the experiment, to put the experiment and the researcher and the potentiostat all in the best position to make the best measurement possible. And so when we talk about instrument properties, we talk about acquisition mode, electrometer modes, E&I filters, and bandwidth limit. And you can see by default many of these are kind of set to an auto function, and then those are different depending on whether we're operating in energy actions or corrosion or physical electrochemistry techniques. So this is a key reason why we may have a better setup for the VersaStat to make a constant current charge-discharge experiment than we would using this similar signal type as a chronopotentiometry in a physical electrochemistry package or the galvanostatic action within the corrosion setting. Let's talk about how we apply these other types of techniques and show some of the data. We talk about some charge-discharge step. This is a two-step constant current experiment. We can simply use a positive current to charge a battery just like it was plugged into the wall, and use those electrons to move the lithium ions around and drive the battery up to its positive cutoff potential. And so this is going to be commonly 4 point something volts for a lithium ion battery, or 1.4 volts for nickel metal hydride. Then what I'm going to do is I'm going to discharge the battery. And so I'm going to use a different polarity of current. So the current's going to have to drive an opposite flow of current. And then I could discharge at the same current that I charged at, or a different one, commonly 3.5 volts. And so you can see kind of what that looks like on the left, and then what it kind of looks like on standard discharge curve on the right. This is what it would look like as a potential versus time driver. I told you earlier you can start seeing how we get more and more complex experiments, and we can start doing techniques such as charge-discharge with voltage hold. So this is going to be a CCCV because it's a constant current, constant voltage action. So when after I reach the charge cutoff, what this does is it's going to hold that amount of charge. So now, hold that voltage as charge continues to accumulate in the battery. So basically, I'm stuffing all those interstitial sites with the lithium ions and making sure they're completely full state before I start the discharge process. And so what I like to show here is, instead of potential versus time, I'm going to show this as potential versus absolute value of capacity. And so I have the capacity on the x-axis here, which is functionally time multiplied by the applied current. But what this does, it allows you to show that when we have the accrue Q set to yes, I can see that I would have normally around the 780 or so milliamp hour mark at 3.8 volts. Without this step, I would start the discharge process immediately after reaching that. This is going to hold that there, and you can see allow the charge to continue to accumulate. And we have the option there through that accrue functionality whether you want that to be additive to the charge from the charge step. Most people do. We also have some advanced signals and data capture available through the energy techniques that are just not available through physical electrochemistry or corrosion methods. And so this is if you want to charge and discharge your battery based on constant power or constant resistance. And so if you can think about how this works, think about power as the example, and power is the product of voltage times current. And so as I'm discharging the battery in a constant current, galvanostatic mode, I use a very small current when the voltage is very high, a steady current through the plateau of the discharge, and then an increasing current as the voltage of the battery drops. And to do that, that really provides your device from the battery at a constant power. But you need it's a feedback mechanism within the potentiostat and the software control package that tells the potentiostat what value of current to apply to maintain that constant power. Very similar experiment type through resistance, but it's the ratio of voltage and current instead of the product of voltage and current. We have other techniques such as galvanostatic intermittent titration technique and potentiostatic intermittent titration technique. This is GIT and PIT. Different types of applications, but the key application for these two is trying to measure that diffusion coefficient of the lithium ion through the solid state of the different electrode materials. And that's very important as we try and facilitate pulse power. One of the things we can do is try and engineer a electrode structure that fluidly moves these lithium ion batteries, these lithium ions, through those sites to provide the highest levels of efficiencies. Delta functions. These are really, if you think about kind of a measure on change, and so what this does is it's constantly looking at the data coming back from the VersaSTAT, but it's only recording data when there's a big change, when there's a significant change, and you get to decide through delta E or delta Q what that significant change is. So basically I'm oversampling and I'm looking for when there's a change, and that allows me to capture data very quickly when the voltage changes a lot, but not so much in those plateaus. and these experiments may be hundreds or thousands of cycles, and data files can really become huge if you want the high data acquisition rate. This allows you to look at that function, to look at that data, but really only record when there is a significant change. So after the data is acquired, we can move over to some specific graph templates and data types for popular battery analysis. Top left-hand corner here, I have a potential versus capacity, and those are the charge and discharge steps. And you can kind of see as the battery continues to be charged and discharged through the cycles, you see a little bit of decay in the amount of capacity it can deliver on the discharge step, and that's the capacity fade of the battery, and that's what you would expect to see here. Over the right-hand side, VersaStudio, using those techniques, these energy techniques, will go ahead and calculate the capacity versus cycle number for you. And so this is the amount of charge out of a battery on both the charge state and discharge state by cycle. That's based on the size of the battery, so the capacity of the battery that you've put into the instrument properties. Coulomb efficiency, I told you about that early on, is it's a study of the amount of charge into a battery versus the amount of charge I get out of the battery versus cycle life. So let's look at this, and you can kind of see in the first couple of cycles of this test, the Coulomb efficiency was very high. I was getting out basically all the charge I was putting in, and then at cycle 6, I got a significant decrease in the amount of charge out versus the amount of charge I put in. So that tells me that something has gone wrong inside the battery to drive such a significant change in the charge being delivered from the battery. Other types of techniques, other types of graph analysis might be capacity versus time or power versus energy. So we spoke a lot about DC testing methods, and some of the other presentations we'll have will go into electrochemical impedance spectroscopy, and that's really our techniques for solid, that's really a great technique for studying state of charge of batteries. Here's some data that we showed from 18650 at different charge states, and we can kind of go in and monitor the state of charge of lithium-ion batteries. And we'll talk more in a different presentation about how we can apply impedance and how we can apply some of these other products and tests to more advanced studies of lithium-ion batteries. I appreciate your attention today, and if you have any questions about this presentation, feel free to email me at rob.sides@amatech.com. Thank you and have a great day.